let's go ahead and jump into chapter 3. So chapter 3 is a very straightforward chapter. It's equilibrium of a particle. So in a three-dimensional coordinate system, somebody says, sketch a particle. What would it end up looking like? It would end up looking like one of these. What do you call that? A dot, a point. A particle just is a point or a dot. It's just defined by not a size, but a location. Okay. And what we're going to do is we're going to do the equilibrium of the particle. What do you think about equilibrium? Is it going to accelerate? No, the statement of equilibrium is that the sum of the forces is equal to 0. And so our criteria for the equilibrium is sum of the forces equal to, here, got to write it the correct way, the sum of all of the forces are equal to 0. Now, we're going to do it in 2D, coplanar, then we're going to do it in 3D. You have to trust the math more in 3D. But you might as well start writing things in vectors. You can do vectors in 2D and vectors in 3D, Cartesian vectors. So that's why I said the sum of the forces must be equal to 0. There's one little itty-bitty thing wrong with the equation that I wrote. Can you see, is it with the left-hand side or with the right-hand side? Where is my little itty-bitty, trivial error that I have made? How about a clicker, A or B? Let me change this over. Do you see what I'm asking? Sometimes I write things and it's incorrect. Thank you for correcting me when you do it in class. It helps me stay on track. But something's missing. Something's wrong with this equation. In the next 18 seconds, can you tell me if it's either left hand or right hand side? All right, we're out of time. Let's see what we got for results. All right. So what's wrong with the right-hand side that I left something out? No. Okay, but okay. What we're going to find is that we're going to have a vector equation for equilibrium that'll be 1. And then we'll have scalar equations for equilibrium. In 2D, there'll be 2 scalar equations. In 3D, guess how many scalar equations? 3. Meaning the sum of the forces in the x and y and z all have to be precisely equal to 0. So this is the little trivial thing. I left out this. And in the book, you'll see it. It's like, hold it. They'll write that equation in vector form, and then they'll write the scalar equations, and there'll be slightly different notation. And so what is this trying to designate? That it's not equal, a vector equation needs to equal a vector on both sides of the equation. And so it's 3 zeros. 0i, this equation is 0i plus 0j plus 0k. And then you're going to get 3 scalar equations. This chapter is relatively straightforward. It's just now using all of chapter 2. And what did we say about chapter 2 mathematically? You have to be correct. It's challenging there. So let's press forward. So the equation's equilibrium, it's not Newton's second law. It's not Newton's third law. It's Newton's first law that says this: for an object at rest or in a state of motion where it's not changing its state of motion, the sum of the net forces or all the forces on it is equal to 0. So the sum of the force is equal to 0. And then we're going to get the big FBD. And when I teach statics, I often stress the number one complaint of the faculty teaching solid mechanics or fluid mechanics or any other follow-on class, dynamics. The number one complaint does say, oh, Monteufel, you taught statics. Let me tell you how worthless you are as an instructor, because all the students that got A's in your class, they came into my class, and guess what they cannot draw? A free body diagram. And if you look through the book, you'll see again and again where it's stressed, you must draw a free body diagram in order to, Anyway, you've got to get the free body diagram right. I always build up like this is very, very, very important. Then you get to chapter 3 and they say, all right, free body diagram. We're going to get to the real crux of this class. But really, the book doesn't say it, but it's really the free point diagram because everything's a particle. You don't have bodies. You don't have dimensions yet. That's the next chapter after we get moments of forces. So it's a little bit of a letdown to really call it a free body diagram. It's a free point diagram or a free particle diagram at this point. But anyway, what does the word free mean? You isolate or cut it or isolate it from the surroundings. And it's very clear what is the focus of the study. What am I analyzing? It's not this plus a lot of other stuff. It's only this. And everything else is in the surroundings. And so we need to then really concentrate and be clear in our sketches and illustrations and our free body diagrams. What are we analyzing and applying the sum of the forces equal to 0 to? All forces need to be included. And if somebody says, oh, the students can't draw a free body diagram correctly, what are they really saying? You left off some very important forces. You left off weight. You left off a reaction force. You weren't able to draw the tension correctly or the friction correctly or something like that in your free body diagram. That's really what they're going to complain about. Anyway, let's jump into 2D problems. Here's a problem. It's just like problems. I can open up any Physics 1 textbook that you use. Calculus base, university physics. It'll be just like this. It'll be just like this. So let's jump into it. We have ropes. What do you think a rope can do? You can do one thing with the rope really well. Pull on it. Can you push a rope? Nope, nope, nope. So, can a rope be in compression? Nope. Can a rope be in tension? Absolutely. And so this is almost too intuitive. I don't know how to explain it any more than that. But we have these ropes or chains or cables, and they can only be in tension. They can only be in tension. Next we'll get to a rod or a strut, which could be in both tension and compression, but for ropes and that, only in tension. Now, what we have is we have a rope that's connected to this as a ring right here. And this ring, one of the ropes goes up and goes right over this. What do you think the name of this thing is called? It's a pulley. A pulley. Now, do you think it's a very heavy, rusted bunch of friction pulley or idealized frictionless pulley?
The rusted pulley.
No, not the rusted pulley. The frictionless pulley. What do you think that means about the ease at which that pulley could rotate if it had a little force imbalance and it, tried to pull it and it would rotate one way, true? Or it would rotate the other way. So if it can easily rotate this way or that way, guess what the tension is of the rope going around the pulley? Continuous, or do you think it's going to change the tension? The tension is going to be the same. The tension of a rope going around a frictionless pulley does not change. So, if I cut the rope right here and I threw away this and I focused on the end, I would say I'd have to pull down in tension on the rope right there with the magnitude of the tension in the rope. If I cut the rope right here and I threw away this, I'd have to be pulling down in that direction. If I cut the rope right here, it'd be having to pull back in that direction. I'd have to be... Now, we didn't say the vector, we just said the magnitude of the force, which is called tension. Because didn't we just change direction of the cable? Sure. So one thing is the tension is the same anywhere. Here's another rope segment. And when you're brand new to these, sometimes I'll tell students, just color code that rope. All right. Now, is that red rope the same rope as this purple rope that goes down to crate B? Yes or no? No, because something happens right here. The one rope ties into a ring, and the other rope ties into a ring, and that ring is not a rope, it's a ring. They tie into the ring. All right, so how many unique ropes do you see in this problem? Are there 1, 2, 3, 4, 5? Are there 5 unique different tensions in ropes in this problem? Are there 4? Are there 3? Are there 2? Are there 1? How many tensions do you see? Unique ropes with unique tensions in them. Clicker question, huh? Should I do that?
Yeah.
Ease, that'll help because I beat you up on the last one. There's either 1, 2, 3, 4, A, B, C, D, 5, E. All right, multiple choice. How many unique tensions in ropes are we talking about? All right. So there are 3 unique ropes. And those students that are playing with me with the answer B and E, look at color code. Like I'll try and encourage you to do again is maybe get a thick marker, maybe color this one red, and it goes like this. That's rope 1. Here's another rope. Color coded that one already. Color code that blue. Color code this rope purple. There's 3 unique ropes. They all join at the ring. They tie into the ring. Rope here ends at A, crate A. This one ends at crate B. This one ends at crate C. All right. All right, let's press forward. So the crate A has a weight of 225 pounds. Professor, you made a big deal about pound mass and pound force, and I'm just so confused. Is this a mass of crate A equal to 225 pounds, lb, or is it the weight of crate A equal to 225 pounds? I don't know. What is it?
The weight.
Is the weight. All right. They didn't show me a gravitational force vector. They kind of get tired and they would clutter up the book. Which way is the gravitational force vector? Down. It's the way the weight, it's the cable's being straight down, right? Holding up the crate. All right, so this is the weight of A is 225 pounds. Okay, can you tell me what is the mass of that crate?
225 pound mass.
Yeah, I want it in pound mass. Let's go ahead and do it. It'll be the mass of crate A will either be 225 times 32.2, 225, or 225 divided by 32.2. All of these are the magnitude, and each are the unit pound mass, not pound force. Pound mass, pound mass, pound mass. I'm going to start it. There you go. All right, I'm trying to give you softball questions. I'm not trying to hurt you. I'm trying to really okay. Anybody wait till your parent? All my kids are gone. The youngest is in the Army somewhere for 2 years now already. So almost all my children are older than everybody in this room. But when I did it, the little T-ball. You put the ball right there on the stand. They walk up there. You get them all situated. You say, smack the ball. Anybody go play T-ball? Anybody watch T-ball? Anybody? I mean, it's the game is not to try to strike out the batter. T-ball is to let them put it in the play. This was a let them put it in the play. All right. I don't know where I'm going wrong. If I buy 10 pounds of potatoes at the store, is it 10-pound mass or 10-pound weight? They're the same. It's 1 for 1. Now, if you move to the earth, off the earth, you move to the moon, now you're going to have a different G, blah, 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 and all that story. All right, I got to stop all these I was hoping that would build up your confidence, but I need to move on. Then we have crate B is 300 pounds. And the system has this cable going over to crate C is 45 degrees. That's a given. They define this angle theta as the cable going off from the horizontal off to crate A. And they want you to calculate the weight of the crate C and the angle theta. So the weight of the crate C is unknown and the angle theta. How many unknowns are there? Mathematically. if you're going to have a chance of getting to solve for two unknowns, do you think you can do it with one equation? No, from math, how many equations do you think you need? Two independent equations, like algebraic equations, okay? All right, so where are we going to get our two independent equations from? We're going to get them from a free body diagram. All right, but there's a number of free body diagrams you can do. Do this one. If I do a free body diagram around this crate A, think about having to enclose crate A in a circle or a sphere or some other shape that completely encloses it. In 2D, it's just a circle. I had to cut something. I had to cut the air, but the air doesn't exert a net force on it. All right? I had to cut this cable right here, did I not? When I cut the cable, and the focus of the study is what's inside the cable, the surroundings affect the inside of the cable by pulling up. That would be the tension in my cable A. Does that make sense? All right, maybe you have to repeat that to yourself. Now we also have the weight of the crate A acts. It's a body force. It acts on it. So you think, this is a great, I wish this whole class was this easy. If I do the sum of the forces in the y direction, usually y is up and x is horizontal, what do you think in the y direction, sum of the forces in the y direction has to be equal to 0? Guess what we conclude? TA acting up is equal to WA acting down. The tension in the cable equals the weight of the crate. It's almost too obvious. It's like trying to explain something. All right. Now, I could go over here and I could do a free body point diagram of the ring. True? I isolate it. I bring it over here. This is my free body diagram of the what? The ring. R-I-N-G. I can spell ring. There you go. And now I have a force going up, a force going up. Why? Because I had to cut the cable. I had to cut the cable. The cable's in tension. It's the surroundings is pulling up on that segment of the cable. And then I have a cable pulling down. All right. We did a free body diagram right here. There's a lot of free body diagrams you can do. For crate B, it's got the weight of B. This is the tension in the cable going up. So this is the tension in the cable coming down, which is the same as the weight of B. Why not just skip that whole step and just call it the weight of B? You're absolutely right. But maybe you need to draw multiple free body diagrams and slowly dissect this problem. And now we're going to have the tension going over in cable to lift cable C or hold up cable C, and the tension going over to hold up cable A. Are these two magnitudes the same in different free body diagrams? Yeah. You know what? You could replace that by the weight of the crate A. How about if I come and do a free body diagram of crate C, and I have to cut right there at that cable that's holding up crate C? I conclude that. So some people are probably saying, hey, you're slowing me down. Come on, this has got to go faster or something. But my three forces are the weights of the crates when I focus on the free body diagram at the ring. All right. Now we have this orientation of 45 degrees and an orientation theta. Before I spend more time on the correct free body diagram, which will give me the answer, the ring free body diagram, I want to come up here and I want to do a pulley free body diagram. You know, you're an inquisitive student. You say, I love these free body diagrams. Hey, let's do one of the pulley. Well, it cut right here through the cable, did it not? And it cut right there through the cable. But what else did it cut right through? The steel shaft holding the pulley to the roof. Well, what would happen if the steel shaft broke? Just intuitive. What happens if the steel shaft broke? it would no longer be able to be in tension. The thing would fall, wouldn't it? Well, then it wouldn't be in equilibrium. For it to be in equilibrium, the steel shaft holding it to the roof is going to be in tension. True? But a lot of people, they say, oh, you want a free body diagram of that pulley? I know how to do ropes. And that's it. And it's incomplete. And that's why the dynamics instructor or the solid mechanics or the fluid mechanics instructor is going to complain to me. They're going to say they can't. They missed a force, an important force. Here you might want to say, well, it's some sort of tension in the shaft holding it to the roof. All right. But so whenever you do a free body diagram, be very clear. Go a complete 2D, go in a circle, or 3D, go in a sphere to encompass it, and be careful of where you're cutting. What are the boundaries? All right. Now let's go back to the one that's going to pay great dividends and answer our question. Here's our free body diagram of our ring. What did we do to the ring? We collapsed it to a point because it's a particle for our analysis. Could you analyze a car as a particle for an analysis? Yes, you could. You could even analyze the earth as a particle for an analysis. It's just on all your perspective. You could analyze a book as a particle for some point. Or you may need to take into account the dimensions of the earth or the dimensions of the book or the dimensions of the ring or anything else. But here we are. Let's just do it. I need to do equilibrium. Sum of the force is equal to 0. You're going to have an x equation for equilibrium, and you're going to have a y equation for equilibrium. So you bust it. You say, this is my coordinate direction, y. This is my coordinate direction, x. Now, you can do it in a couple steps because I'm fighting for space. Let me just say it like this. I'm going to pick off the x component of the tension in the cable C, which is equal to the weight of C. So it's the weight of C times the cosine of 45 degrees. Is that the component in, I'm dissecting it into this, right, into x. Likewise, over here, we can put minus the weight in the cable going to B, which is equal to the weight of B, times the cosine of theta. Does this force, which is equal to the weight of the B crate, does it have any component in the x? No. So we end our equation, it's equal to 0. Well, I'm doing a right triangle right here, and this is my right triangle. Remember, right triangles aren't always simple. I mean, you flip them around and change their orientation. And this is my opposite, this is my adjacent, this is my hypotenuse. And so this is my tension, is the weight of B. So the weight of B is right. And then I have the cosine of an angle measured right here. And I'm going to put a negative sign in here. Oh, what you may be thinking of, let's start all angles from the positive x and go that way. Well, okay, that's a different theta than sketched. And if you did it that way, then you could get rid of the negative sign. But please, we'd like our math, but let's not do that. Let's stay with the theta angle. Theta is defined. Okay. Does that equation look good or not? No wonder you're staring at me like I'm crazy. This is A, and that's A. Now you got double thumbs up. Now you're ready to go. Thank you.
We're all wondering why you're using B.
I don't know. You have to correct me when I'm wrong.
We tried.
You tried?
Yeah, he was like, shouldn't it be weight A? And you're like, well, it's just B.
You got to be a little more persistent or something. Let's write it now for the y direction. In the y direction, we have the weight of A times the sine of theta pulling up. We have the weight in the cable we're going to see, WC, times the sine of 45 degrees going up. And if you want, you can put the WB going down on this side, or you can put a negative WB equal to 0, whatever you want. Now, this is what I like to do. I like to walk through the equation and say, okay, the weight of B, you know what? That was 300 pounds. True? That's like a check. I got that one in my equation. The weight of C, no, that's something I'm looking to solve for. The weight of A, you know what? I've got that. That's a check. How about the weight of C? No, that's something I'm looking to solve for. How about the theta? Something I'm looking to solve for. Theta, something I'm looking to solve for. Weight of A, check. So I look and I count my equations, 1 and 2, and I count my unknowns, theta and weight C, and I say, somehow it's possible. Mathematically, it should be good to go. When I took statics, I would spend an hour or two chasing my tail, going in circles. I'd get one equation, and then I go, I'll rewrite one equation like it's a second equation, but it isn't a second equation, it's the same equation. And then I would try and solve for two unknowns. Have you done something like that? Yeah, I have. Please, so if you can go methodically through it. Now, how are you going to solve this problem with two equations, two unknowns? Some people go like this. I'm kind of bored. We'll call in the mathematicians and be done with it. No, you can't do that. You have to solve it yourself. So I know that this is now just more math review. Let's rewrite the equations. So we have the weight of C is unknown. We have the cosine of 45 minus the weight of A, 225, times the cosine of theta is equal to 0. And then I'm going to have the weight of A, 225, times the sine of unknown theta, plus the unknown weight C, sine 45, equal to the weight of B, 300. Somebody want to suggest a strategy? Usually we try to manipulate one of the equations to isolate and eliminate to get one equation with one unknown. So for the first equation, maybe I'll do this. I'll say, look at WC is equal to 225 cosine of theta divided by the cosine of 45. Did I do the math okay? Now I substitute that into the second equation. So we have 225 times the sine of theta plus, hey, that's where we substitute the WC. We're going to substitute 225 cosine of theta, sine of 45 divided by the cosine of 45, and all that's equal to 300. Do we see how we substituted? And then you say, okay, guess what? I have now just... this is, did I erase a number? This is supposed to be 300, isn't it? So now this is 300 divided by 225. And then I'm going to have the sine of theta plus the cosine of theta times the tangent of 45. True, false? Sine over cosine is tangent of 45? Does this give me the tangent? And I make a brilliant observation, or allow a student to make the brilliant observation, that the tangent of 45 is 1. So if with the tangent of 45 is 1, then the sine of theta plus the cosine of theta is equal to 300 over 225, which I believe is 1.333 ad nauseum, right? We got one equation, one unknown. Can you solve it? I'm going to pause. I'm going to walk around. I'm going to see if you can solve it. Let me ask one question. You could have approach A or approach B. Approach A would be analytical, or B would be numerical, right? Either approach A, analytical, or approach B, numerical. Let's see which one you like. Answer clicker A or B. I just want a poll. It's not graded. Just, do you think you can solve this problem analytically? Or you think it would be best solved numerically? Everybody's in. All right, let's take a look. Again, I'm not going to grade it. But, so let me help you. Go numerical. Since about 1950 something, there's a thing called a computer that's been invented. A lot of our textbooks don't recognize it. A lot of our faculty don't recognize it. But guess what this is part of? The computer revolution, the calculator. There was a time when it was all slide rule. That was even before my time. But how would you do this? Not analytically, but numerically. So, all right. So we had one student solve this numerically using the calculator, and the theta comes in at 25.5 something, around 25.5 degrees. Now you can do it, and I encourage you also do this by hand. And so make a little table of theta and guess 10. And then compute the sine of theta plus the cosine of theta. That's what your calculator is going to do when it iterates. It's going to numerically go through. How many people have taken numerical methods? 2173. 1, 2. That's it? Oh, well, you're going to take it. They're going to cover this. You're going to say, hey, I know how to solve. I know why you cover this now. I was struggling in statics. And you're going to say, oh, secant method or Newton-Raphson or some other technique that they cover. So then you plug it in. If you plugged in 10, you would get this as 1.158. Now, does that equal 1.333? No. Okay, let's try 15 degrees. 1.2247. Is it going in the right direction? Yeah. All right, then you try 20. Then you try 25. 25 comes in at 1.329. Now you're close. And now what you can do is you say, I'm tired of guessing. Why can't I use the last few evaluations to get the better next guess? Newton-Raphson or secant. It all makes sense. You're going to do a little linear interpolation, straight line between the last two guesses. Let me write in 20 for you. It's 1.2817. And you want it to be 1.3333. You try 26, I've got 1.337, and so it's right in there. I rounded off 25.5, be done. Once I have 25.5, that was part A or half of the problem. I have to go back and get the weight of C, crate C. Where do I go back to? Right there, right? So you go back to the equation and you calculate the weight C, and you already got it? 287 pound. Makes sense? And this one I would box it for the final answer. 3 significant digits. There you go. Okay, that took more time than I thought. Let's press forward. So we covered cables, we covered pulleys. They're all frictionless. We don't have any friction-filled pulleys. They're all frictionless. They rotate easily. And the tension in the cable is, as it wraps around that pulley, is the same. It's constant tension. All right. Oh boy, now we're going to have to cover springs. So, if you have a spring, what do you remember about a spring? What is this K for that spring? What is that? Spring constant. And so if you wanted to know the force in the spring, this spring is going to be the spring A to C. I'm going to take the K of that spring, and I'm going to multiply it by what? Okay, is it going to be the current length of this spring? Length from A to C? Or is it going to be the length minus its unstretched length? And this really is only the stretch of the spring. You have a spring, it's in equilibrium, there's no pull, tension or compression, it has a given length. I try and pull it, I get a force, right? So if I have a spring just sitting here, there's its unstretched length, LAC naught, and then I pull it, maybe I move it out here, that's LAC, the current length. Guess what? This is the distance of the stretch distance, or compression distance if it's negative stretch. And then this would be the force to say, hey, I have to have the force to stretch it. And these springs, people have used, done calculations with a spring. All hands go up, or you go get your refund from your physics instructors. Give me your physics book. I'll show you springs, okay? We're going to be good at springs as well as right triangles, okay? As well as free point diagrams. All right, so now we have two springs. They're used to support the 150 kilogram crate. Did they give me the weight of the crate or the mass of the crate? They give us the mass of the crate. How am I going to get the weight of the crate? Multiply by 9.81 and call it a Newton, right? Weight is mg. All right, and a Newton is a kilogram meter per second squared. This is all easy stuff, but don't trip up on that. So we're going to get the weight of the crate. Determine the stretch in the spring A to B and A to C. So here is the A to B spring and the A to C string. What do you think we're going to do? You can do this, you can do this. You can get this is a trick here. What did I just do? I got a free point diagram of something that's pretty large, but I'm going to collapse it to a point. And it'll be simply the weight down of the crate. It'll be a tension force in the spring A to C, and a tension force in the spring A to B. Does that make sense? But that's or you do it this way. You don't draw the big circle that way. You just draw a little circle here, and then you did a free body of the crate, and you know that the weight of the crate is the tension in this cable coming down from that joint of the two springs. All right, so this is my F. Well, I'm going to do an equilibrium. I'm going to have the sum of the forces in the X. Might as well introduce a coordinate system. X is common in the horizontal and in the Y, vertical. Okay, that makes sense. Two equilibrium equations, sum of the forces X, sum of the forces Y equal to 0. I probably want to decompose the force A to C into X and Y component. What allows me to decompose it? What information is available on this illustration? How about you do this? You give me the equilibrium equation in the X direction and the Y direction, given the F A to C is an unknown, and F A to B is an unknown, and even use symbol weight where it's going to be calculated, but just use the symbol weight, and any other information. You need to use the spring constants yet. I first get the forces. Once I get the forces, then I'll come back and get the stretch. That'll be easy. All right? Let me walk around and make sure you can do it. Please go fast. I'm going to cover a lot of material. All right. And so in the interest of time, I'll pick it up here. What I want to do is I want to basically use or introduce a triangle that's like this. It's a right triangle, and it's similar to my direction of the force vector. So I introduce these similar triangles. One is geometrical in nature. And I look and I say, oh, you know what? This has to move over a horizontal distance of 4 meters. And in that, it's going to rise 3 meters. Oh, this is one of my favorite triangles. It's a 3, 4, 8 triangle. No, not a 3, 4, 8. It's a 3, 4, 5. How did you get to 5? Where does a 5 come from? 5 is the square root of 3 squared plus 4 squared. This is a 3, 4, 5 triangle. And now you get used to it. You come over here and say, oh, I'd like a similar triangle for this one. And so the horizontal is a 2. The vertical is a 3. Oh, this is a 2, 3, 4 triangle. Is this a 2, 3, 4 triangle? No, it's not. It's a 2, 3 square root of 13. Absolutely good. Somebody back there had it, which is brilliant, I thought. Or you've seen it before, maybe. I don't know. Or you read the book. Did I encourage you to read the book? Yes. Please read the book. You may get something out of it. All right. So the square root of 13. So when I come over here and I want to pick that off, these are my little triangles to help me. 2, 3 square root of 13. This is 4, 3, 5. So for the x, I'm going to have the force AC in the positive x and only the 4/5 component of it. And in the negative, or I just put it on the other side of the equal sign, it's going to be the force in the spring AB times 3 divided by the square root of 13. This is only the second week of this class, Professor. You are moving at lightning speed. Sorry, that's a 10-week class, isn't it? So let's just keep going. What about in the y? We're going to have 2 up. We're going to have force in the AC that's going up, and it's just 3/5 of that. And we're going to have the force AB going up, and we're going to pick off, did I mess that up? I messed it up, didn't I? It's a 2/13, isn't it? And then going up, it's a square root of 13. True? No. Thank you. Did I correct myself? Kind of nice when I can stop making errors. And that's equal to the weight. Okay. How many unknowns are there in this problem? Force AC, force AB, the weight. We know the mass of the crate. We know these ratios. 2 equations, 2 unknowns. I wish I could spend more time, but you just need to be able to solve for the force AC, and that comes in from my notes to be about 0.8175 kilonewtons. And then the force AB is not the same. It's 1.176 kilonewtons. Did I get those right, or did I change my notation? AC. Do me a favor, check these to make sure they work. How would you check them to make sure they work? Plug them into one of the equations. Can you run it for me? Let me get 5 people to confirm with a thumbs up when they confirm it. 2 yeses, 3 yeses, 4, 5, 6, 7. Very good. Okay, we can go on. Now, once I have those, I come back and I use the stiffness in the spring to get the stretch. So that's what we want, the stretch in the spring. So let me write it up there down here. Let me scoot down. So the stretch in spring A to C is that tension force we just calculated divided by the stiffness of the spring A to C. That's a C, not an S. And then the stretch in A to B is the force in A to B divided by the stiffness in the spring A to B. And those come in, they're very small numbers. Let me scroll down. The stretch A to C comes in at about 2.73 centimeters. And the stretch A to B comes in at 5.9 centimeters. All right? Let me just scroll up a little. As soon as I scroll down, I know I just messed it up for somebody. I messed it up for you. Good? All right. Thank you very much. Let's press forward. So, reviewed about springs. There's somebody's law. What's that? Hooke's law. And that's how we deal with springs. Springs can be either in tension or in compression. You just have to worry about buckling on a spring if you have it in compression. Once you get good at 2D, you march off into 3D. And when you get into 3D, you still have Newton's first law, the sum of the forces equal to 0, but now we bust that one vector equation into how many scalar equations? 1 for the x, 1 for the y, 1 for the z, 3 scalar equations. Somebody says, you should make them do everything in vectors. That's fine, but look, you're going to decompose it into I, j, k. So, anyway. This is a tough problem. I don't think I'm going to have enough time to go through it. Let me just talk to myself, and you please listen. This is called the traditional lecture. All right? The rig consists of 2 struts. Okay, so this is strut 1. It comes up here. And here's the second strut. This is in 3D, so it's really hard to see. the strut 1 starts at this location B and ends at this location A. And the strut 2 starts at location C and ends at A. A strut, is that a rope? No, a strut, you can either pull it or compress it. It can be in tension or compression. Now, if you put it, it's a long, slender strut, just like some other things. If you compress it too much, it can buckle. Next class, not this class. Aren't you glad? So no buckling in this class. All right. Now, it's used with a cable. So this is our cable over here. It comes up to point A and pulls down to point D. That's our cable. And it's used to lift something heavy, a 200-kilogram crate. All right. Determine the compressive force in each of the struts. So this strut is going to be in compression and the other one's going to be in compression. Can you see that it would make sense that it would be in compression? And then determine also the tension in the cable A to D. So 2 compressions, 1 tension. Assume the force in each strut acts only along its axis. It's just straight along its axis. All right? Focus my analysis on a point, a particle. That's the most logical point. Everything seems to converge at that point. And when I come off of it, it's really hard to draw it in 3D, but I'm going to try. I'm going to have something coming down. I can't forget the weight. I cannot forget the weight of the crate. The weight of the crate is mg. You know, I can express that as a 3-dimensional vector, true? So if I wanted to, maybe I'll say the force as a vector of the weight, it would be 0 in the I, 0 in the J, because this is the X direction, this is the Y direction, this is my positive Z direction. Gravity is acting straight down, and it would be minus W in the K. True or false? Look good? Yeah, that's good. So that's one of them. Then we know that they give us the information that the strut is in compression and compression. So the strut ends at the point. So sometimes they'll draw the force vector of the compression force in the strut ending at that point. True? Or somebody could say, it's just like this. I like to put the beginning of each force at the point. And so I move this force to there, it's mathematically the same. And I move this force to there, it's mathematically the same. But be careful when you have forces pushing onto a point, not pulling from a point. It's more common that they're pulling from the point. All right, now I have one more. Let me try and draw it. I'm going to draw it like this and then like that. And then I have one more, which is the tension in the cable, like that. Now, again, I isolate that point to get my free point body diagram. And do I have all of them? Is my free body diagram correct? I have weight, I have a force in the compression, let's call it the force in the strut C to A, the force in the strut B to A, and then the tension, which is a force going from A to D. Did I miss anything? Pause at this point, because don't go marching further on if you didn't get the correct free body diagram. I think that's all. We already got this weight. Here, let me draw it like this. The force, weight coming down, expressed it as a 3D vector. How could I get the force as a 3D vector of the strut compression from A to C? How do I get the force B to A? Did I say C to A or not? I don't know if I misspoke there, sorry. And then the force A to D. Well, it's going to be a constant. This one's going to be the tension in the cable A to D times a unit vector. Going from where? From A to D. I love unit vectors, don't you? We can do it. We can do these unit vectors. What about this one? Well, you can either put, it's going to be, it's probably better to do this unit vector from B up to A. That's easier to do. And so we're going to have the magnitude of the force, or the compression force, maybe I'll use C for compression, BA, times the unit vector from B to A. And then this would be the compression force in the member C to A. and the unit vector from C to A. And what are they asking me to solve for? The compressive force along each of the struts. This is what I'm trying to find. The compression in C to A to C and A to B. All right? In those struts. And then the tension. So those are my three unknowns. Is C, CA, CBA, and then TAD. Those are my three unknowns. Well, three unknowns, I better have three mathematical independent equations. They're going to come from the sum of the forces in the X, sum of the forces in the Y, and the sum of the forces in the Z. How do I get this U, C to A? How am I going to get that unit vector? Get the two locations of the points. Go slow in this. First of all, right here, can you tell me what is, from the information given, it's 4 meters here, this is 4 meters here. Okay, can you tell me what is the XYZ location of point A? 0? 4, 4. Very good. Location of point B. So this would be like A. Get the location of point B. 2, 0, 0. How about the location of point C? -2, 0, 0. And the location of point D? -5.6 meters, yeah. 0, 0. Now that I have those two, did I do it right? X is, yeah. So there you go. Thank you very much. I did that on purpose. No, I didn't. 0, -5.6, comma 0. There you go. Now, once you have the locations, you get the displacements. So going from C up to A, that would be moving how much? You'd move +2 in the X. This would be, sorry, I've got to do it in 2 steps. Do R, C to A, which is moving up +2 in the X, moving up +4 in the Y, and moving up +4 in the K. Then I get the unit vector C to A is equal to, what is the magnitude of the 2, 4, 4? This would be 8, that would be 16, 16, 32, 32 plus 4, 36, divide square root of that, 6. So it'll be 2, 6I, 4, 6J, 4, 6K. That's this one. How about the next one? You do the same thing and do the same thing. Okay, in the interest of time, I'm going to speed up a little bit. So then we do the sum of the forces in the X, and then the Y, and then the Z. You'll get equilibrium equations. You'll have 3 unknowns. We know which are the 3 unknowns, and you'll be able to solve this problem. I can't finish it in time, so let's call it a quits. Thank you very much for your attention.
All right, so I ran out of time in lecture, so I'll finish up this problem in my office. What we need to do is we need to get that unit vector from B to A, and is going to be -2/6 in the I, +4/6 in the J, and +4/6 in the K. And likewise, the unit vector from A to D, let me scroll up a little bit, and so that one from A to D, this one starting up here, it's going to be nothing. Let me draw it. U, A to D will be 0 in the I. It'll be -9.6 in the, divided by the magnitude, which you'll calculate to be 10.4, in the J, plus, minus 4 over 10.4 in the K. So a little bit of work to get that unit vector from A to D. Well, once I have the 3 unit vectors, that's calculated correctly, then I'll come down here and I'll get my sum of the forces in the X equal to 0. So what we get is that compression in the member. I've been calling it either member A to B or member B to A. To me, that you know, isn't that important for the unit vector. It's very important because that has direction, but it's just the magnitude of the compression. So this will be the compression member A to B. That's this strut A to B times negative 2,6 plus the compression in member CA or AC times 2,6 equal to 0. All right, well, right away what you're going to see is these magnitudes cancel and these compressions are equal. And the problem is symmetric, so that those struts have the same amount of compression. That's what comes out of that first equation. All right, let's go to the second equation, the sum of the forces and the y. We'll have the compression A to B times 4/6 plus the compression A to C, and that's 4/6 plus, well, I'm going to put the tension in B to D times a negative 9.6 divided by 10.4, and I ran out of room. Of course, I always run out of room. Let me kind of move this out of the way. I don't want to really erase it. Just move it out of the way, and we'll come back here, and that sum's equal to 0 in the y. All right, and then for the sum of the forces in the z, the compression member A to B times 4/6 plus the compression A to C times 4/6 plus the tension in this tension goes from A to D. A to D is negative 4 over 10.4 equal to 0. Now I have 3 equations and 3 unknowns. At this point, we just need to be able to solve for the 3 unknowns, and the tension in the member A to D will come in at 3.644 kilonewton. Oh, I forgot. I have the weight here. Without the weight, there isn't much happening, and we calculate that weight, which is the product of 200 times 9.81 in the units there. And so if you wanted to, you could just move this over to 0.2 and then put a kilonewton right there. Kilonewton. All right, so anyway, it comes in, tension A to D comes in at 3.644 kilonewtons, and then the compression in A to B, which is the same as the compression A to C, have the same value, 2.523 kilonewton. Little sloppy, but I'm just going to call it quits and finish the problem. Thank you very much.